Hello, in this lecture we'll answer two questions. In the first question, we'll find out the area of this semicircle that is inside quarter circle A or B. And in the second question, we'll find out the area of this green shape that is inside rectangle ABCD. So we'll start with the first question. So in the drawing, we have a quarter circle. A or B is a quarter circle. We actually know that AO equals to 5 units in its length. That is to say, the radius of this quarter circle is equals to 5. And in addition, inside this quarter circle A or B, we have this semicircle, and our mission is to find out the area of this semicircle. So first of all, we'll define the center of this semicircle. This point is point C. Likewise, we will define the touching point of this quarter circle with this semicircle. This point is point F, and we will define the touching point of the quarter circle with the semicircle. This point is point G. And we will define the point of tendency of tangent AO with this semicircle. This point is point H, and finally we will define the point of tendency of tangent BO with this semicircle. This point is point L. In addition, we will define the radius of this semicircle as x. Therefore, CF equals to CG. They are both the radii of this semicircle, and according to our definition, the radius of the semicircle equals to x. So CF equals to x, CG also equals to x. In the next step, we will join point C and L together by a straight line. CL is of course the radius of this semicircle, that is equals to x according to our definition. Likewise, we will join point C and L together by a straight line. CL is also the radius of this semicircle, that is equals to x. So here we have the radius CL that is equals to x. The radius CL is drawn to point L, that is the point of tendency of tangent BO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius LC. If BO is perpendicular to LC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius CH of this semicircle. The radius CH that is equals to x is drawn to point H, that is the point of tendency of tangent AO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius HG. If AO is perpendicular to HG, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So, by doing these constructions, we already have quadrilateral CHOL. Inside quadrilateral CHOL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral CHOL we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, not a square. So we relate to this quadrilateral CHOL as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CHOL, side CH must be equal to the opposite side OL. But CH is x, therefore OL must be also equal to x. Likewise, according to the sum rule, in the sum rectangle CHOL, side CL must be equal to the opposite side OH. But CL is x, therefore OH must be also equal to x. So we found out that quadrilateral CHOL is not a rectangle but a square because of the fact that all of its sides are equal to each other. Each side of this square is equal to x. In the next step, we will join points O and C together by a straight line. By joining points O and C, we get the right and associated triangle, triangle CLO. In the next step, I will copy this right and associated triangle, triangle CLO in a new page and we will implement the Pythagoras theorem on this right and associated triangle, triangle CLO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a relation from Pythagoras theorem. So actually, this is the right and associated triangle, triangle CLO that I call it from the original drawing. According to the Pythagoras theorem, in this right triangle CLO, CO square equals to CL square plus LO square. So I'll write it down. So CO square, that is the square of the hypotenuse, equals to CL square plus LO square. CO is the missing side, so we leave it as it is. So CO square equals to CL square. CL is x, therefore CL square is x square plus LO square. LO is also x, therefore LO square is x square. So in total, we should find out that CO square equals to x square plus x square. X square plus x square is 2x square, so we should find out that CO square equals to 2x square. Here we take a root out of this equation, and finally we get that the length of the hypotenuse CO is equals to the square root of 2 times x units in its length. So here CO equals to the square root of 2 times x units in its length. We know that point O is the center of the quarter circle. So from point O, that is the center of the quarter circle, we have line segment OC that bisects chord FG. Why line segment OC bisects chord FG? Because CF equals to CG equals to x. So line segment OC bisects chord FG into two halves. Each half equals to x. And therefore, we can implement here rule 7. So I'll repeat quickly on rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisects the chord, then the line segment is perpendicular to the chord. So in the drawing we have a circle. This is point O, that is the center of this circle. So from point O, that is the center of the circle, we have line segment OM that bisects chord AB. That is to say, MB equals to MA. And because of the fact that line segment OM that is run from the center of this circle bisects chord AB, line segment OM will be also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule 7. So we can actually implement rule 7 in our drawing. Why? Because in our drawing, from the center of the quarter circle, that is to say from point O, we have line segment OC that bisects chord FG. That is to say, CF equals to CG equals to X. So line segment OC bisects chord FG into two halves. Each half equals to X. So all the requirements of rule 7 are satisfied, and therefore we can implement rule 7. According to rule 7, line segment OC will be also perpendicular to GF. If OC is perpendicular to GF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 7. In the next step, we'll join points O and F together by straight line. We know that the radius of this quarter circle equals to 5. Why? Because AO equals to 5, and AO is of course the radius of the quarter circle. So now we know that the radius of the quarter circle equals to 5. What is the definition of line segment OF? Line segment OF starts from point O, that is the center of the quarter circle, and then at point F, that is the point on the quarter circle itself. So this is exactly the definition of a radius. Therefore, OF is the radius of this quarter circle, is equals to 5. In the next step, I'll copy the right angle triangle CFO in a new page, and we will implement the Pythagoras theorem on this right angle triangle CFO. Here by PT is a relation from Pythagoras theorem. So actually, this is the right angle triangle CFO that I copied from the original domain. Side CF equals to x units in time, side CO equals to the square root of 2 times x units in time, and the hypotenuse FO equals to 5 units in time. It is actually the radius of the quarter circle. So according to the Pythagoras theorem, in this triangle CFO, the square of the hypotenuse is FO squared, and it must be equal to FC squared plus CO squared. So I write it down. FO squared, that is the square of the hypotenuse, must be equal to CF squared plus CO squared. FO, the hypotenuse FO is 5, therefore FO squared is 5 squared, that is 25. And it is equals to FC squared, or CF squared. CF is x, therefore CF squared is x squared, plus CO squared. CO is equal to 2 times x, therefore CO squared is 2x squared. So in total, we actually found out that 25 equals to x squared plus 2x squared. X squared plus 2x squared equals to 3x squared. So if we found out that 25 equals to 3x squared, here we divide this equation by 3 and finally get that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. What is the area of the semicircle? We know that the radius of this semicircle is x. Therefore, the area of this semicircle must be pi x squared over 2. So write it down. The area of the semicircle, the area that we are looking for, that is to say the area of the semicircle, is equals to pi times x squared. Pi x squared over 2. Look at again. The area of this semicircle, of course, equals to pi x squared over 2. This is the area of the circle over 2. It is pi x squared over 2. So the area of the semicircle is pi x squared over 2. So it is actually pi over 2 times x squared. And x squared is 25 over 3. Therefore, we substitute x squared in this equation by 25 over 3. And we get that in total the area of the semicircle equals to, in the numerator we have 25 pi. In the denominator we have 2 times 3, that is 6. So in total the area of the semicircle equals to either 25 pi over 6 square units, or in terms of numbers, this equals to 13.09 square units. Repeat again, I should found out that the area of this semicircle equals to either 25 pi over 6 square units, or in terms of numbers, the area of this semicircle equals to 13.09 square units. So we finished with the first question. In the next step, I will present you the second question and we will solve it. Our mission in the second question is to find out the area of this green shape. So in the drawing we have rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units in its length. In addition, inside this rectangle ABCD we have this semicircle and this quarter circle. Quarter circle PC and this semicircle. Again, our mission is to find out the area of this green shape. So in the first step, we will define the radius of this semicircle as x. So BC, that is the radius of this semicircle, equals to x according to our definition. We also know that all the angles inside any rectangle are right angles. Therefore, this angle is a right angle. It's 1 out of 4 angles inside rectangle ABCD, and therefore it is a right angle. Likewise, we also know that in any rectangle, the opposite sides of rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 5, therefore DC must be also equal to 5 units in its length. So I write it down. Side DC equals to 5 units in its length. Likewise, according to the same rule, in the same rectangle ABCD, side BC must be equal to the opposite side AD, but BC equals to x according to our definition. Therefore, AD must be also equal to x. AD is one side of rectangle ABCD, but AD is also the diameter of this semicircle. So we know that the diameter of this semicircle equals to x. If the diameter is x, the radius must be equal to half of it. So the radius is x over 2. So the radius of this semicircle is equal to x over 2 units in its length. We will define the center of this semicircle, this point, as point O. So the radius OA of this semicircle equals to x over 2 units in its length. And the radius OD also equals to x over 2 units in its length. So in the drawing we have an external knot between this semicircle and this quarter circle. That is to say, they touch each other externally in this point. We will define their touching point, this point, as point S. And whenever you have an external knot between two circles or semicircles or quarter circles, you can implement rule 10. So I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. So in the drawing we have two circles and they touch each other externally at this point, point P. So they have an external knot between them at point P. The center of this circle is here at point O. The center of this circle is here at point M. And the straight line that connects the centers together is of course the straight line OM. According to this rule 10, the straight line OM must pass through point P, that is their touching point. Again, the straight line OM must pass through their touching point, that is point P. Or OPM is one straight line. Again, according to rule 10, OPM is one straight line. So we can implement rule 10 in our drawing. Why? Because in our drawing, we have an external knot between this semicircle and this quarter circle. That is to say, they touch each other externally at this point, point S. And therefore, we can implement here rule 10. The center of this semicircle is here at point O. The center of this quarter circle is here at point C. And the straight line that connects the centers together is of course the straight line OC. And according to rule 10, the straight line OC must pass through their touching point, that is point S. Again, the straight line OC must pass through point S, that is their touching point. Or OSC is one straight line. Again, according to rule 10, OSC is one straight line. So we join points O and C together by straight line. And according to rule 10, the straight line OC must pass through point S, that is their touching point. It is very easy to see from the drawing that the straight line OC passes from point S, that is their touching point. If OSC is one straight line, it means that if OSC is one straight line, it means that OC must be equal to OS plus SC. Again, OC equals to OS plus SC, according to rule 10. So OC equals to OS plus SC. OC equals to OS. OS is the radius of this semicircle, that is equals to x over 2. So here OS equals to x over 2 plus SC. SC is the radius of this quarter circle, that equals to x. So in total we have found out that OC equals to x over 2 plus x, that is 1.5x, or 3 over 2 times x. OC equals to 3 over 2 times x units in its length. So I'll write it down. Here OC equals to 3 over 2 times x units in its length. So in the next step, I'll copy the right triangle ODC in the new page and we'll implement the Pythagoras theorem on this right triangle ODC. Here by PT is the progression for Pythagoras theorem. side OD equals to x over 2 units in its length. Side DC of triangle OCD equals to 5 units in its length. And we just right now found out that the length of the opposite OC is 3 over 2 times x units in its length. So actually, this is the right triangle OBC that according to the original drawing. According to the Pythagoras theorem, in this right triangle ODC, OC squared, that is the square of the hypotenuse, must be equal to OD squared plus DC squared. So I write it down. So OC squared, that is the square of the hypotenuse, equals to OD squared plus DC squared. The hypotenuse OC is 3 over 2 times x, therefore OC squared is 3 over 2 times x squared, that is 9 quarters times x squared, and it is equals to OD squared. OD is x over 2, therefore OD squared is x squared over 4 plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. If we found out that 9 quarters times x squared equals to 1 quarter times x squared plus 25. Here we subtract x squared over 4 from this equation, and we get that 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared, and it is equals to 25. 8 over 4 is 2, so in total this expression equals to 2x squared, that is equals to 25. Here we divide this equation by 2, and finally we get that x squared equals to 25 over 2. Here we take a root out of this equation, and finally we get that x equals to the square root of 25 is 5 over the square root of 2. So in conclusion, we found out that x equals to 5 over the square root of 2, and x squared equals to 25 over 2. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawings it's very easy to see that the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. Again, the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. So I write it down. The area of the green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. Because again, we actually found out that the area of the green shape in total equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So what is the area of rectangle ABCD? We know that the area of any rectangle equals to the length of the rectangle times the width. The length is AB, that is 5, the width is BC, that is x. So in total, the length times the width equals to 5x. So the area of rectangle ABCD equals to 5x minus the area of this semicircle. We know that the radius of this semicircle is x over 2, and therefore the area of this semicircle must be equal to pi times x over 2 squared divided by 2. So the area of the semicircle in total equals to pi times x over 2 squared, that is the square of the hypotenuse, divided by 2, minus the area of this quarter circle. What is the area of the quarter circle? We know that the radius of this quarter circle is x. Therefore, the area of this quarter circle must be equal to pi x squared over 4. So I write it down. The area of this quarter circle equals to pi x squared over 4. So in total, the expression that is inside between those two brackets is the area of the green shape. So what is the value of this expression? This was actually to 5x minus, here we have x over 2 squared is x squared over 4. So in total this expression will be equal to minus pi x squared over 4 times 2. Okay, minus pi x squared over 4. So the area of the green shape in total equals to 5x. Here we have minus pi x squared over 4 times 2, that is 8. So in total the area of this expression, in total the value of this expression is minus pi x squared over 8. Here we have minus pi x squared over 4. Here we multiply both the numerator and the denominator of this expression by 2 in order to a common factor with this expression. After we multiply it by 2, we get that this expression in total will be equal to minus 2 pi x squared over 8. So the area of the green shape in total equals to 5x. Here we have minus pi x squared over 8 minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So in total, if we found out the area of the green shape, the area of the green shape equals to 5x minus 3 pi over 8 times x squared. But we already found out that x squared equals to 25 over 2 and x equals to 5 over square root of 2. Therefore, you can substitute x, this expression, by 5 over square root of 2 and x squared in this expression by 25 over 2. We do it now and we get that the area of the green shape in total equals to 5x, and x is 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared is 25 over 2. So in total we found out that the area of the green shape equals to 5 times 5 is 25, so in total this expression equals to 25 over square root of 2 minus this expression. In the numerator of this expression we have 3 pi minus 25, that is minus 75 pi, divided by 8 times 2 is 16. So in total the value of this expression equals to minus 75 pi over 16. So in conclusion, we found out that the area of the green shape equals to 25 over square root of 2 minus 75 pi over 16 square units. In terms of numbers, the value of this expression in total equals to 2.95 square units. And that is the answer to the question. Repeat again, we found out that the area of this green shape equals to 2.95 square units. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our mission was to find out the area of this semicircle. that is inside quarter circle A or B. So in the drawing we have quarter circle A or B. We know that the radius of this quarter circle AB equals to 5 units. Inside this quarter circle we have this semicircle, and our mission is to find out the area of this semicircle. So in the first step we define the center of this semicircle. This point is point C. Likewise, we define the touching point between the semicircle and the quarter circle. This point is point F. And we define the other touching point of the semicircle and the quarter circle. This point is point G. We also define the point of tendency of tangent BO with this semicircle. This point is point L. And finally, we define the point of tendency of tangent AO with this semicircle. This point is point H. In addition, we define the radius of this semicircle as X. Therefore, CF equals to CG, the above the area of the semicircle, this is equal to X according to our definition. So CG equals to X, CF equals to X. In the next step, we join point C and L together by straight line. CL is of course the radius of the semicircle, that is equal to X according to our definition. Likewise, we join point C and H together by straight line. CH is also the radius of the semicircle, that is equals to X. Here we can implement rule 1, because we have the radius CL that is equals to X. The radius CL is drawn to point L, that is the point of tendency of tangent BO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius LC. If BO is perpendicular to LC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have here the radius CH is equals to X. The radius CH of this semicircle is drawn to point H, that is the point of tendency of tangent AO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius HC. If AO is perpendicular to HC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the same rule, rule 1. So actually, by doing those constructions, we actually created a quadrilateral HCLO. Inside this quadrilateral HCLO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this professing angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this professing angle must be equal to 90 degrees in its size. So inside quadrilateral HCLO, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle, not a square. So we relate to this quadrilateral HCLO as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle HCLO, side HC must be equal to the opposite side LO. But HC is X, therefore LO must be also equal to X. Likewise, according to the same rule, in the same rectangle HCLO, side CL must be equal to the opposite side HO. But CL is X, therefore HO must be also equal to X. So actually found out that quadrilateral CHLO is not a rectangle but a square. Why? Because of all of its sides are equal to each other. Each side of this square equals to X. In the next step, we join points O and C together by straight line. By joining points O and C, we can get here the right and associated triangle, triangle CLO. In the next step, I copied this right and associated triangle CLO in a new page, and we implemented the Pythagoras theorem in this right and associated triangle CLO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right and associated triangle CLO that I copied from the original drawing. In this right triangle CLO, according to the Pythagoras theorem, CO square, that is the square of the hypotenuse, equals to CL square plus LO square. Again, CO square equals to CL square plus LO square. CO is the missing side, so we will leave it as it is. CO square equals to CL square. CL is X, therefore CL square is X square plus LO square. LO is also X, therefore LO square is X square. So in total, CO square equals to X square plus X square, that is 2X square. So CO square equals to 2X square. Here we took a root out of this equation, and finally found out that CO equals to the square root of 2 times X units in its length. Okay. So here, CO equals to the square root of 2 times x units in its length. Point O is the center of the quarter circle. So from the center of the quarter circle, that is to say from this point O, we have line segment OC that bisects chord FG. Why line segment OC bisects chord FG? Because it divides chord FG to two halves. Each half equals to x. CF equals to x and CG also equals to x. And whenever you have a line segment that is drawn from the center of the circle and bisect the chord, you can implement rule 7. So I repeat quickly on rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisects the chord, then the line segment will be also perpendicular to the chord. So in the moment we have a circle, this is point O, that is the center of this circle. From the center of the circle, that is to say, from this point O, we have line segment OM that bisects chord AB. That is to say, MA equals to MB. And now you have a line segment that is drawn from the center of the circle and it bisects a chord like in this drawing. Then line segment OM will be also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule 7. So we can actually implement rule 7 in our drawing. Why? Because in our drawing, from the center of the quarter circle, that is to say from point O, we have line segment OC that bisects chord GF. That is to say, it divides chord GF into two halves. Each half equals to x. CG equals to x and CF equals to x. So all the requirements of rule 7 are satisfied and therefore we can implement rule 7. According to rule 7, line segment OC will be also perpendicular to GF. If OC is perpendicular to GF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 7. In the next step, we join points O and F together by side line. We know that the radius of this quarter circle is 5. So what is the definition of OF? OF is also the radius of the quarter circle. Why? Because it starts from point O, that is the center of the quarter circle, and S and point F, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OF is the radius of the quarter circle, that is equals to 5. In the next step, I copy this right green triangle CFO in a new page, and we implemented the Pythagorean theorem in this right triangle CFO. So okay, this is the right and green triangle CFO that I comment on the original drawing. Side CF equals to x, side CO equals to the square root of 2 times x units in its length, and the hypotenuse FO equals to 5. According to the Pythagorean theorem, in this right triangle CFO, FO squared, that is the square of the hypotenuse, equals to FC squared plus CO squared. Again, FO squared equals to CF squared plus CO squared. FO is 5, therefore FO squared is 5 squared, that is 25, and it is equals to CF squared. CF is x, therefore CF squared is x squared plus CO squared. CO is square root of 2 times x, therefore CO squared is square root of 2 times x squared, that is 2x squared. So in total, we shall find out that 25 equals to x squared plus 2x squared. X squared plus 2x squared is 3x squared. So we shall find out that 25 equals to 3x squared. Here we divided this equation by 3 and finally found out that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. What is the area of the semicircle? We know that the radius of this semicircle is x. Therefore the area must be equal to pi x squared over 2. And again, the area of the semicircle must be equal to pi x squared over 2. So it is pi over 2 times x squared. And x squared is 25 over 3. Therefore we substitute x squared in this equation by 25 over 3 and finally found out that the area of the semicircle equals to pi over 2 times 25 over 3. So in the numerator we have 25 pi, in the denominator we have 2 times 3, that is 6. So in total the area of the semicircle equals to either 25 pi over 6 square units, so in terms of numbers, the area of the semicircle equals to 13.09 square units. I repeat again, the area of the semicircle equals to either 25 pi over 6 square units, so in terms of numbers, the area of the semicircle equals to 13.09 square units. So we finished with the first question. In the next step, I presented to you the second question and we solved it. In the second question, our mission is to find out the area of this green shape. So in the drawing, we have rectangle ABCD. Inside, we know that side AB of rectangle ABCD equals to 5 units in its length. In addition, inside this rectangle ABCD, we have this semicircle and this quarter circle. And they touch each other externally at this point S. Again, our mission is to find out the area of this green shape. First of all, we define the radius of this quarter circle as x. So BC, that is the radius of this quarter circle, equals to x according to our definition. We know that the angles in any rectangle, all the angles are right angles. So this is 1 out of 4 angles inside rectangle ABCD, and therefore it is equal to 90 degrees in its size. In addition, we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC, but AB is 5, therefore DC must be also equal to 5. Likewise, according to the same rule, in the same rectangle ABCD, side BC must be equal to the opposite side AD, but BC is x, therefore AD must be also equal to x. So AD, that is one side of rectangle ABCD, equals to x, but AD is also the diameter of this semicircle. So we know that the diameter of this semicircle equals to x, and therefore the radius must be equal to half of it. So the radius is x over 2. So the radius of this semicircle is x over 2 units in its length. The radius OA, point O, is the center of the circle, the center of the semicircle. So OA is the first radius, that is x over 2, and OD is the second radius of this semicircle, that is also equals to x over 2 units in its length. Okay. So in the drawing, we have an external notch between this semicircle and this quarter circle. That is to say, they touch each other externally in this point S. Whenever you have an external notch between two circles, or semicircles, or quarter circles, you can implement rule 10. So I'll put quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes for their touching point. In the drawing, we have two circles, and they touch each other externally, this point P. The center of this circle is at point O. The center of this circle is at point M. And the straight line that connects their centers together is, of course, the straight line OM. And this straight line OM must pass through point P, that is their touching point. Again, this straight line OM must pass through their touching point, that is point P. Or OPM is one straight line. Again, according to this rule 10, OPM is one straight line. So I can actually implement rule 10 in our drawing. Because in our drawing, we have an external notch between this semicircle and this quarter circle. That is to say, they touch each other externally at point S. And therefore, we can implement here rule 10. The center of this semicircle is at point O. The center of this quarter circle is at point C. And the straight line that connects their centers together is, of course, the straight line OC. And this straight line OC must pass through point S, that is their touching point. Again, according to rule 10, this straight line OC must pass for their touching point, that is point S. Or OSC is one straight line. Again, OSC is one straight line. If OSC is one straight line, it means that OC must be equal to OS plus SC. Again, OC equals to OS plus SC. OC equals to OS. OS is the radius of this semicircle, that is x over 2. Plus SC. SC is the radius of the quarter circle, that is x. So in total, OC equals to x over 2 plus x, that is 3 over 2 times x units in its length. 1.5x or 3 over 2x units. So if you found out that the length of OC is 3 over 2 times x units. In the next step, I copied the right triangle ODC in the new page and we implemented the Pythagoras theorem on this right triangle ODC. So actually, this is the right triangle ODC that I copied from the original drawing. Side OD equals to x over 2 units in its length, side DC equals to 5 units in its length, and the hypotenuse OC equals to 3 over 2 times x units in its length. According to the Pythagoras theorem, in this right triangle ODC, OC square equals to OD square plus DC square. OC is 3 over 2 times x, therefore OC square is 3 over 2 times x squared, that is 9 quarters x squared. And it is equals to OD square. OD is x over 2, therefore OD square is x squared over 4 plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So in total we found out that 9 quarters times x squared, 9 quarters times x squared equals to 1 quarter x squared plus 25. Here we subtracted x squared over 4 from this equation, and finally found out that 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared. Here x squared over 4 minus x squared over 4 is 0, and we left only with 25. In conclusion, we found out that 8 quarters times x squared equals to 25. 8 over 4 is 2, so this expression equals to 2x squared, so 2x squared equals to 25. Here we divided this equation by 2 and finally found out that x squared equals to 25 over 2. Here we took a root out of this equation and finally found out that x equals to the square root of 25, that is 5, over the square root of 2. So in total we found out that x squared equals to 25 over 2 and x equals to 5 over the square root of 2 units in its length. Our mission is to find out the area of this green shape. What is the area of the green shape? From the drawings it's very easy to see that the area of this green shape equals to the area of the rectangle ABCD minus the area of this semicircle minus the area of the quarter circle. Repeat again, the area of the green shape. The area of the green shape in total equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. What is the area of rectangle ABCD? The area of any rectangle equals to the length of the rectangle times the width. The length is AB, that is 5, the width is BC, that is x. So the length times the width is 5x. So the area of rectangle ABCD equals to 5x minus the area of this semicircle. We know that the radius of this semicircle is x over 2, therefore the area must be equal to pi times x over 2 squared divided by 2. So the area of the semicircle equals to pi times x over 2 squared divided by 2 minus the area of this quarter circle. The radius of this quarter circle is x, therefore the area of this quarter circle must be equal to pi x squared over 4. Again, the area of the quarter circle equals to pi x squared over 4. So the expression that is inside between those two brackets is the area of the green shape. What is the value of this expression? It is equals to 5x, and here we have x over 2 squared is x squared over 4. So in total, this expression equals to pi x squared over 4 times 2. Pi x squared over 4 times 2. Minus pi x squared over 4. Minus pi x squared over 4. So the area of the green shape equals to 5x. Here we have pi x squared over 4 times 2 is 8. So it is minus pi over pi x squared over 8. Here we have minus pi x squared over 4. Here we multiplied both the numerator and the denominator of this expression by 2 in order to have a common factor with this expression. After we multiplied both the numerator and the denominator of this expression by 2, this expression equals to minus 2 pi x squared over 8. Minus 2 pi x squared over 8. So the area of the green shape in total equals to 5x. Here we have minus pi x squared over 8 minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So in total the area of the green shape equals to 5x minus 3 pi x squared over 8. But we have already found out that x squared equals to 25 over 2 and x equals to 5 over square root of 2 units in its length. Therefore, you can substitute x in this equation by 5 over square root of 2 and x squared in this expression by 25 over 2. We did it and we should have found out that the green shape in total equals to 5x and x is 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared is 25 over 2. So in total we should have found out the area of the green shape equals to the value of this expression, that is actually 5 times 5 is 25, so in total this expression equals to 25 over square root of 2. Here we have in the numerator of this expression we have minus 3 pi times 25 is minus 75 pi. In the denominator we have 8 times 2, that is 16. So in total this expression equals to minus 75 over 16. In total the area of the green shape equals to 25 over square root of 2 minus 75 pi over 16 square units. And the value of this expression in terms of numbers, this expression equals to 2.95 square units. So if we found out the area of this green shape equals to 2.95 square units. Okay, thank you very much.